So I understand that the recording, the Microsoft Teams meeting recording of the first lecture that I gave for CNL on January 21st, basically that was only audio captured. So what I'm going to do now is just simply run through the lecture very quickly to give the participants some record of how the audio might fit into the actual visual part of the presentation. I'm doing this simply on PowerPoint record mode, and as with the other recording, there is no chance that, in fact, that any embedded media is captured. So the video clips, which I sent to Heidi Norden separately as YouTube videos, you'll just have to insert them or realize where they go. If you have access to them on YouTube, you have to see where they go as part of the presentation. Okay, so let's get going. I don't want to spend too much time because these will be very large files. So the first lecture has to do with crystal structure and introduction to the diffraction principles. So as part of crystal structure, I'm also going to be talking about defect structure, because defects have an important role to play in microstructure analysis, of course, and that's something that is part of the business. In order to understand defects, and when I say defects, I mean dislocations, twins, primarily, in crystalline materials, you need to have an idea of the crystal structure, what it is, why materials deform in particular ways. So we're going to start with crystal structure. For anybody studying crystals, crystallography, the first fundamental thing that you get introduced to, I think, are basically the types of crystals that exist. And the way to describe them, or historically the best way to describe them, has been in the form of Bravais lattices. The Bravais lattice is an infinite array of discrete points generated by a set of translation vectors in 3D space. I'm just reading off the text here. There are 14 different configurations in which they can be arranged in the crystal. And the smallest unit, take this body-centered cubic unit, for instance, be repeated in an array to make up the full crystal is called a unit cell. So basically you take this unit cell and you translate out in any one axis or all of the axes and just reproduce it. And that is then the crystal. The important thing about a Bravais lattice that's critical here is it forms, it can be described by a number of point groups, and what the point group means is that if you take any one point, we take any atom, or this, in this particular instance these are points, but really they're atoms. You take any one atom, and when you've built up your lattice and you look around you, you look in all directions, for any one atom, it should, the environment should appear the same. You should have another atom that's a certain distance away in one direction, a certain distance away in another direction. And that would be the same whether you take one of the corners of the cell, or even if you take one of the, in this case, one of the atoms at the face center. Because when you've built up, when you created a structure from all of these, in fact, even though you have a layer which ostensibly appears different from another layer, it is the same, but it's just shifted a little bit. But ultimately, you will always, if you pick any atom, you will always find 4 other atoms in this plane which are at the corners of the square in this particular case, around that atom. So even if you pick this atom here, you'll find four other atoms too, and then two out here that are in the same arrangement around that atom. And that's essentially what it means. You don't have to get too much detail about that. Just to know what it is. So I mean, you really not going to be having to deal with Bravais lattices or definitions or anything like that, but you will come across it. You will come across people talking about Bravais lattices, and the main thing is to understand and realize, as many of you will, that there are different crystal classes: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and this is what they are. For all intents and purposes, for much of the work that gets done at CNL, certainly in my historic experience, there have been three crystal structures that have dominated in terms of work that one has to do, research one has to do at the lab. They are the BCC structure, the FCC structure, and the hexagonal close pact. The BCC is less important than the other two, but BCC is the beta phase. It's the structure of the beta phase in zirconium pressure tubes. And in zirconium pressure tubes, you have a hexagonal close packed alpha phase interspersed with filaments or layers of body-centered cubic beta phase. So that's why these two crystal structures are here amongst the ones that you will likely come across the most. Hexagonal close packed, of course, is the lifeblood of the CANDU industry, because CANDU reactors are made from zirconium alloys because they run on natural uranium, and zirconium is the best material to use, which has high strength, good corrosion properties, and has a low neutron absorption cross section. So CANDU reactors have to be made from zirconium. Otherwise, they wouldn't run. We wouldn't be able to preserve the neutron economy. Neutron economy is very important in CANDU reactors because they're running on dirt you dug out of the ground. I mean, they're running on natural uranium. Very important structure that you will have to work with often. FCC applies mostly to steels. So austenitic stainless steels, the most common steel used in the nuclear industry is 304 stainless steel. 316 stainless steel is also used. They're austenitic because they have enough nickel in them that they are FCC phase. So if you were a body, oh, actually, yeah, that's a good point. If there was low nickel, you'd be body-centered cubic. So low alloy steels, the material that makes up feeders, as an example, and pressure tubing in light water reactors is primarily a body-centered cubic, although they're often, even in the FCC steels, there may be a little bit of BCC because it's a multi-phase, multi-precipitate kind of structures, often different engineering alloys. So I omitted to say that. So in the BCC case, yeah, feeders are low alloy steels are BCC. End fittings are a ferritic martensitic steel. So a ferritic typically is BCC as well. Martensitic can describe a number of different types of phase transformations that make the structure one of these or something different. And I'll talk about that later on in this lecture. Okay, so these are the three main crystal structures you're going to be interested in, apply to most nuclear reactor components. The point to note here is that the hexagonal close packed structure is not a Bravais lattice. And that's simply because if you take any one point, you can't say that the environment is exactly the same if you look around. That's all. The hexagonal close packed material is defined by its space group symmetry. And in the case of the hexagonal close packed materials, they have a space group symmetry of p63 slash, and the slash means it's a perpendicular to MMC, this sort of thing. Okay, and MMC are two mirror planes and a C-axis glide plane. So we'll talk about that in a second. Okay, Miller indices. This is something you're going to have to be familiar with. You'll come across it a lot. You'll see planes and directions described by a set of numbers. I'm going to start with how to define a plane formally. You may already have come across this in your undergraduate days or whatever, or at college or whatever. So the formality of it is in order to describe a plane, you have a, let's say we have a cube, and you want to consider this plane here in blue. What you do is you take the intercepts along the different axes. Let's say we have lattice parameters. That's the, if you like, the point spacing. If it was a point, if you were to consider it as a point group, the atom spacing is A, B, and C. You take the intercepts in terms of the lattice sum value, which is basically the fractional, ultimately the fractional intercept with in terms of the lattice parameters. So we have three lattice parameters, A, B, and C, which define the size of the cube, the spacing of the atoms. We take the reciprocal of the intercept with respect to the lattice parameter, and then we have a set of numbers, 1, 1, 0. And in this particular case, this is the lowest degenerate form of this description, simply because all the numbers are already integers. So the prime goal in deriving Miller indices for a plane is that it should be indexed according to just simply integers. So we have no fractions. There's no room for fractions. So in this particular case, the intercepts are at 1 on X, 1 on Y, and basically 0 on C. So what that means is really an infinite. It intersects at infinity, but in terms of the lattice parameter, you can just see it by inspection. One knows that that's a 1, 1, 0, because it doesn't intersect with the C-axis. Likewise for the 2O. 2O simply means it intersects halfway along the X, which is what this indice would refer to. It's halfway between, or at A over 2, if you like, and it intersects with, we're interested in this plane, which is represented by what's shown in red here, which intersects the x-axis at a point A over 2. And then that because of the reciprocal, that is known as a 2O Miller indexing. So basically, when it comes to crystallography, you don't have to do all these intercepts. You can do it in your head easily. But for simple planes like this, for instance, the 100 would simply be this plane here. 200 is our planes that are spaced, halfway along the unit cell. 300 would be, there'd be planes that are spaced at 1/3 of the spacing along the x-axis, on a third A upon 3, spacing of A upon 3 along the x-axis. So you'd have And that's how you would uh, basically assign, know what planes you're looking at. Here's a slide just to show what it might look like if you have what appears to be an irrational plane, but it's not really. It's just that you have to describe it in terms of Miller indices with a higher number, larger numbers, larger integers. In this particular case, we have a plane that intercepts at 3A, 2B, 2C, reciprocals 1/3, 1/2, 1/2. We have to make that integer. The only way to make that integer by multiplying throughout by applying that to all of the indices is to multiply by 6, and then that becomes 233. So that plane is 233. The normal to the plane in a cubic system always has the same integers as the plane itself, and you can see by inspection that well, it's not very clear here, but that direction, the vector would be 2, 3, 3, the normal to this plane. Here's some other examples. There's the one, the 2O I was mentioning about. Bearing in mind, when you say something like a 2O plane, it means every plane which has a spacing which is halfway along the A parameter. Here's some other examples, and this illustrates what I was just talking about there. When we talk about 1-1 planes, in a unit cell, there's room to put 2 of them in there. And the same thing for this 1 or 2. But it basically refers to one may be interested in a particular plane in space at a particular location, but often one's describing a group of planes in the crystal that have a particular orientation. Hexagonal structure is one that you have to be familiar with. If you're working at the lab and say hexagonal close packed structure is very important because it's the one that applies to zirconium alloys, and zirconium alloys are very important for the CANDU system. Hexagonal unit cell is slightly different. We're looking down on the unit cell here along the c-axis. I can't reverse this, unfortunately. In the record mode, I can't reverse, go back along to look at previous slides. But imagine that we have a cell, and I'll show you in the 3D in a minute. You have a cell like this, and we're looking down one axis, the c-axis. We're looking down the axis of the hexagonal cell, and the smallest part of the unit cell is actually this kind of rhombohedral shape. And we have atoms which are at every corner of the rhombohedron, and an atom here which is halfway up and equidistant from these 3 atoms here, but there's nothing there in that part. I'm going to get into this, how you define what this cell is. But the thing about the unit cell in the hexagonal case is that the basis vectors that describe the unit cell are basically and not orthogonal. They're not at 90 degrees to one another. Typically, you would have, if this was the 2 basis vectors along x and y, then this vector here would be 1, 1, 0. You'd be 1, 1, 0. And we'll talk a little bit more about that next. Because the hexagonal unit cell is what it is, and you have this non-orthogonal basis. What that means is that if you just use two indices or two basis vectors to describe or, fundamentally three basis vectors, A1, A2, and an upward drawn normal, call it Z. But we're looking down along the Z axis. And in a three index system, a Miller system, we'd only have A1 and A2 as the basis vectors to describe directions and planes in that unit cell. So let's think about directions, because that's easier now. If we think about directions, in the three index system, which is basically, and we're looking down on the units along the z-axis. In the three index system, using x1 and x2, you would have for x1, for A1 we'd have 10, for A2 we'd have 010, but for this one A3 we would describe that as -1, -2, minus A1 minus A2 to describe x3. So it was recognized, I guess, early on that these are equivalent directions in the hexagonal cell, but they have a non-equivalent indexes. So at some point, I assume these guys got together, or somebody decided we're going to make it a different system. We're going to make it a 4-index system, which means there's 4 basis vectors to describe the unit cell. So we have A1, A2, and we're going to add another one, A3. So A3 is always negative the sum of A1 and A2. It's always that. So it doesn't affect the z-axis, what we call W, in this particular case. If it was a direction, if we were to describe the direction vector in terms of UVW relative to the basis vectors that define the cell, we have it's not affected when you go from Miller to Miller-Brave. So if you apply this convention, which is essentially equivalent to thinking about 3 indexes, you have, and let's say if you wanted to look at this direction, 2 bar 1 bar 10, in the Miller-Brave notation, bar 1 means minus. What we're looking at is that we have, in this particular case, for that direction, we go 2 steps along A1, and we've got, we don't have 2 steps. We're going from here. We have 2 steps along A1, -1 step along A2, and -1 step along A3 relative to these bases. And that's going from this point as the origin. So that vector going from here to here has a direction 2 bar 1 bar 10. If we're interested in this vector, which would be the distance from an atom here and an atom here, it would be 1/3 of that. So 2 bar 1 bar 10 gets us along to this point. 1/3 of that gets us to this point. So you'll come across that a lot in terms of Burger's vectors, or lattice spacing, not lattice spacings, but interatomic spacings. A upon 3, 1, 1 bar 20 is the length of the lattice spacing in the basal plane for hexagonal close packed material. It's about 3.233 angstroms, so, or 0.322 nanometers. That's that. So here's a better or a three-dimensional image of the hexagonal close-packed cell. Those last two slides, we were looking down this axis. We're looking down along the c-axis. So now we're going to bring it into 3 dimensions. And what's interesting about the 3 dimensions in the hexagonal system is we have interesting planes where activity might occur, which are more than one plane on which specific activity might occur. And these are the four main planes that one comes across when studying hexagonals. This is actually a hexagonal unit cell. You can define your unit cell to be larger than the true unit cell, if you like. But the hexagonal form of the base unit is comprised of 3 ombohedral unit cells. And I think I have a slide next which shows what they are. Oh, in first instance, again, in terms of definition of the planes, I forgot to mention this. You apply the same convention as you would in the Miller case to define the intercepts in the Miller-Bravais system. Even though you have 4 indices, you still define the intercepts and the planes in the same sense. One thing to note, whereas in a orthogonal system, the cubic system, the indices of the vector which is normal to the plane has the same indices as the plane. When you go to this Miller-Bravais system, that's not true anymore. The indices, well, not even in the Miller-Bravais, just in, just let's stick with Miller-Bravais. When you have the Miller-Bravais system, the normal to the plane does not have the same indices. The normal to this plane does not have indices 1 or bar 1. It's something irrational, and I can't remember now what it is, but it's some other number. It's 3 or bar 2, 3 or bar 3, 2 or something like that. I can't exactly remember what it is, but that's something to pay attention to. So it's only planes which are actually parallel with the c-axis, the z-axis in this case, or the c-axis. We know that as the c-axis. Planes which are parallel, like this prism plane here, prism 1 plane, they do have indices which are for the plane normal, which are the same as the plane. It only really applies to planes which are inclined to either the basal plane or the prism planes. So in the hexagonal unit cell or hexagonal system, we have this variation in density of atoms on different planes. And this varies depending on what metal you're talking about. And you'll see this often define a parameter called the C/A. That's the ratio of the C-axis to the A-axis in the hexagonal system. For zirconium, 1.593. And zirconium is kind of odd because you can have all kinds of activity, whether it's slip or loop formation on numerous planes. And that has to do with peculiarities and impurity effects and this sort of thing. But by and large, if you have elements like zinc and cadmium that have a very high C/A ratio, so you've stretched the c-axis, what that means is the most close packed plane is basal, and it's always basal. But and ideal packing here is the ratio of C to A if you have if you make up the crystal structure from spherical balls, if you close pack it's the ideal packing arrangement. That's root 8/3. Magnesium is the closest to ideal, 1.623. But what you see is that as you drop below ideal, the prism planes start to become more predominant in terms of activity. This shows up very strongly when it comes to radiation damage. If you look at dislocation, loop formation, and the typical habit planes of dislocation loops, that's where point defects will accumulate in the plane. You'll see a little bit of that in lecture 2. For materials like zirconium, which if you can think of them as having a more squashed C-axis here, in principle, most of the cases, especially when it's pure material, the main habit plane is the prism. So you'll get most, and also the main slip plane is also prism. So you get most activity on these, what's called this is a prism 1 plane. But when you have a very impure zirconium or magnesium or titanium, you might find some additional structures on the basal plane. And that's the peculiarities of the effective impurity in that case. We don't need to get into that. So I mentioned about ideal packing, and the best way to understand structures, crystal structures, and how crystals will deform, how glide operations operate, is to construct ball models. You take a bunch of spheres, assume the atom is a sphere, an ideal structure. It's a spherical horse, if you like, a spherical atom, and we've just piled them one on top of the other. So you can create, and you have 3 options, and I'll show that in the video. You can start with a base layer, this layer here, and then we'll call that the A layer. Then you compile, rather like cannonballs on the deck of a sailing ship of old, stack the cannonballs up on what's called a B site, which is shown here. So we have another layer on top, and whether it's HCP or FCC, that will always be the case. But then you have a choice. The next atom can go there, or it can go there. So in the hexagonal close pack structure, this A site, the site is defined by the location when you look directly down the C-axis. So this A site sits exactly over an atom on the base layer here. This atom here sits directly over that atom there. But you could put the atom here, and that would cover up one of these little holes that you can actually visualize. You can see them going through the structure, and that's shown over here. So you put, in the hexagonal case, you put the next layer, you have 2 layers, and then a third layer. The third layer, you have the option, and if you put it directly above the first layer, that stacking is called ABA stacking. If you put it there, which is not directly above the first layer, that becomes ABC. That's another site, a C site. And then that's FCC. So that's the only difference between hexagonal close packed and face-centered cubic. And it's often very easy. You can understand a lot about these structures just simply by building a ball model or imagining a ball model and then considering how they would things like glide operations, how they would operate. Body center cubic is a little bit strange. It's not close packed. The atoms are like this. They're not stacked like this, like uh, like cannonballs on a deck, and that introduces some peculiarities. But I have videos that are related to this presentation that you can, and now on YouTube, that you can look at. And so for at each point in this presentation, you can just bring up the YouTube video if you're not sure exactly what I'm talking about. It's a good visual guide to actually show the ball models. Another way to look at the structure rather than using that ball model is to just look at the atom sites relative to the unit cell. Unfortunately, I've got the unit cell here. This is actually 3 unit cells in the hexagonal structure, but it helps to see the relative atomic positions of the atoms. So 1 unit cell is really, if I could draw it in here, can I draw it in? I like that. This is 1 unit cell here. Then I can fill in the prism plane here. This is a prism 1 and then prism 2. This volume here, the rhombohedral volume here, is what is the hexagonal unit cell. Face-centered cubic structure. Here's the atoms at the face centers, and because of that, the close packed plane, the one in which we stack up the little table tennis balls, is the 1-1-1 plane. So this plane and then this plane correspond, and then this plane, so that would be A, B, A stacking, is how one would look at the position of the atoms in an FCC structure. BCC, as I say, is different. You just put 4 atoms at the corner and stick one, and another 4 atoms here, and then stick one half in between. So that's not a close packed structure. But there are high density planes in each structure. In the case of the BCC, this is the highest density of planes. And this defines the slip plane, 110. That's, if you remember your Miller indices, 110 plane. And the slip direction, the most common slip direction for slip in BCC is this direction, going from this corner to the middle, or from that middle to that corner. So that is a 111 direction. So the most common slip system in BCC is 111 on the 100 plane. In the case of the FCC, our slip direction is actually across the face, if you like. This is the most close packed direction. This is the shortest interatomic spacing. So we have a slip direction in the FCC case of 110 on a 111 plane. So they're kind of reversed when it comes to FCC and BCC. And in the hexagonal system, in principle, the most common slip system for ideal packing now, and in the case of the Miller-Brave sense, would be one of these directions, one of these A directions which have Miller-Brave indices of 1-1-2. So along one of these dotted lines on this plane. Let me see if I can highlight that. On the 110 plane. So we've got this plane here, and we have a direction here, which is the 1-1-2 direction. Kind of screwed that up, but that's the direction. The length I should have put it here, A over 3. So I just see I've got a mistake there. So let's see if I can draw that. A 3 is the vector. A mistake in the slide, I'll have to correct that. So moving on, again, reminder, what distinguishes the hexagonal close packed face and the cubic is how the atoms are stacked one on top of one another. And the important point is not the first two layers, but the third layer, where you put the third layer in relation to the two layers underneath. And that's all it takes to change the structure, the crystal structure, radically from a hexagonal to a face and a cubic. This is also important when it comes to transformations, because it's very easy to transform from this structure, hexagonal close-packed structure, to a face and a cubic structure. You simply have to take one layer and slide it a little bit. So the next presentation, which won't show up in the video, and I'll skip through, is a demonstration of the hexagonal and BCC close packing. You'll have to watch it on YouTube, but I've got these the links embedded here, but it won't show up in the recording. So to move on, oh, well, I guess you saw those, but to move on, I mentioned often that the unit cell, even though we have an hexagonal structure, and to illustrate the symmetry that one observes for materials like zirconium, we often show the full hexagonal, if you like, base cell, which is comprised of 3 unit cells. And this is actually the unit cell. So it doesn't look like a hexagonal unit cell, but when you appreciate that these 3 are joined together and can create a hexagonal cell, you can see the equivalence of it. So this is just to illustrate what the hexagonal close packed unit cell, not the hexagonal. If that atom was missing, it would be a hexagonal unit cell with that atom there in this intermediate layer in the second plane. This is a hexagonal close packed unit cell. So how do we describe it? Space group. So I can't go back now to that slide because this is a recording, but suffice to say that some crystal structures are simple and you can describe them by symmetry elements like rotation axes or mirror planes or something like this, in terms of describing the symmetry relative to one point going through the cell, and just simple operations like a rotation, a mirror plane. So in symmetry language, we're talking about a mirror plane or a rotation axis, a twofold rotation axis or a mirror plane. The slash here means it's you have one symmetry axis which will be perpendicular to another one. This is a 6-fold rotation, a 3-fold rotation. This bar over the top of something means that's an inversion point. So we can either describe the symmetry in terms of what would be termed simple symmetry operations. That describes the symmetry. So a Bravais lattice, you can describe a Bravais lattice using symmetry elements, which is shown here. But often a crystal structure, you have translations as well. It's not that simple. You can't just describe the structure in terms of simple symmetry elements, and you have to apply other elements. And one is what's called a screw, which is a rotation plus a translation, or a glide, which is a reflection plus a translation. The reason I'm putting this here is to illustrate, or for those new to the business, you will see this often. You might see this often. You might see this notation, P63/MMC, and you might say, what the heck is that? What is that P63MMC? So I'm going to describe that now. So this is in a space group notation. This is how the hexagonal structure will be described, and this is how an FCC structure will be described. Equally complicated. It's strange, eh? Because in terms of stacking up of balls, the actual structure is very simple. But just so you have an appreciation for what space group symmetry refers to, here I've put the main symmetry elements of the space group P63MMC, that slash MMC, in the hexagonal close packed structure. So you can see how the arrangement of the atoms, and this is one unit cell here, how this arrangement of atoms can be described with this collection of symmetry elements. So the first thing to note, the most obvious one and the easiest one to visualize, is the 6-3 part. Now what 6-3 means in the space group notation is it's a six-fold rotation axis, and for each 60 degrees that one rotates, you translate upwards in the direction perpendicular to the plane of the viewing plane of the paper by half a unit cell. So you rotate 60 degrees, translate half. Rotate 60 degrees, translate half. So in terms of the location of this atoms in the unit cell, it would 2 half lattice parameters rotation brings you back into conjunction with the plane of the repeat plane of the atoms in this particular case. Then you do another 60 degrees where translate half, another 60 degrees, translate half. So that brings you back into the edge of the unit cell. So this alternate half unit cell length rotation, coupled with the rotation of 60 degrees at each point, is depicted by this symbol. So this is my unit cell. I have atoms arranged like this. Here's 4 unit cells. I'm looking down on the c-axis, and I have a set of atoms here which are at half the length upwards between these atoms, which are placed directly above each other at a distance equal to the c-axis. So we have one atom on the plane. The next layer of atoms is over here at a half a distance, half the lattice distance coming up out of the paper. And then the next atom we put is back into this position. So it's about equivalent positions, creating equivalent positions in the structure. The dotted line is a glide plane, and what that means is that we can reflect in that plane. So take these 3 atoms here, we reflect them in that plane, take that one to there, and then we translate by half a unit. So that this reflection will take this atom here, but in the plane of the base plane of the basal plane, if you like, but then we must translate it half a lattice distance upwards. So we can get the same effect if we have these 3 atoms here. We can get the same effect with this glide element by reflecting there and translating. Now there's one mirror plane which is perpendicular to the 6-3 axis, and that's the plane of the paper. But then we have these other mirror planes another mirror plane, which is this one, or other mirror planes, if you like, which are shown in here. So we have some mirror planes which are uh, parallel, and some which are perpendicular to the z-axis, to the other rotation axis, or to the primary uh, z-axis of the unit of the system. Yeah. Um, just noticing here whether we have. Well, that's one mirror plane there. I don't want to dwell on this. It's just so that you understand what this means. It's just simply a way of describing how the atoms are arranged in the hexagonal close-packed structure. I mentioned before that this rhombohedral unit cell is kind of really a third of the hexagonal arrangement. And this is the case for a pure material, pure zirconium or magnesium or something like that. But we also get this P63 MMC notation cropping up when you have intermetallic particles. So this one some of you may be familiar with, NBFE2, that's the binary phase of niobium and iron. And it's typically it would form as what's called a Laves phase. And that's the structure. And believe it or not, that is also described by P63MMC. It's not hexagonal close packed, but it has a space group of P63/MMC. It can get complicated. This is something from my undergraduate days that I was involved in my summer project, not my summer project, my third year project. I was working as part of a group of people who were characterizing crystal structures in the chemistry lab, and basically we're using four-circle diffractometer to identify the crystal structure of compounds, and these are organometallic compounds. And the compound itself has the molecules themselves can have an unusual shape, but they're in an arrangement, in a crystal structure arrangement. In this particular case, it's a monoclinic. That just means it's close to, in this particular instance, it's pseudo, it's almost hexagonal, but it's not quite. So that's what a monoclinic system is. And basically what you have is to take into account is the symmetry of the structure, or the cluster, the shape of the cluster of atoms in the molecule, and their orientation within the cell. So in this case, in the monoclinic case, the space group is P. So there's a twofold screw here. That means we can, if we rotate by 180 degrees this cluster and then translate halfway up the unit cell, we go, so that the dark lines here just denote the Z axis location. This is on the base, and this would be upwards. So that twofold axis takes us from here to here. And we could also have a C glide, and the C glide is actually perpendicular, so it's this plane. So we reflect in this plane and then glide. This is that direction. You can reflect in the plane, which is in the plane of the paper, and then glide along here. That's another way to get from this one to this one. Okay, just something to show you, just so that you understand the value, why you have to have space groups, because you can't just simply describe this in terms of simple symmetry operations. So I said how having ball models are useful because that helps us understand deformation. And again, the videos I have attached to this presentation are useful to deformation processes, but they're all done with simple ping pong balls, which are spherical, of course, and what we have is a ideal close packed structure. If we want to look about deformation, the properties of the material are governed to a large extent by the crystal structure, and the properties are often, and we'll see that in lectures 3 and 4, are often, are always, in fact, derived using tensors. But enough of that. I'll explain what tensors are, and it'll be fairly straightforward when we get to that point, for those of you who are not familiar with them. So the crystal structure itself imparts some properties to the material, and it might be isotropic, maybe anisotropic, depending on the crystal structure and the arrangement of the atoms. But defects which are introduced into a material by thermomechanical processing during manufacture or during testing or by irradiation, these also affect the properties. And the way in which the defects are introduced is dependent on the crystal structure, so they're interlinked to some extent. So not only do you have to consider the mode in which you introduce defects, whether you compress a sample or pull it or roll or extrude or whatever, you have to consider the mode at which you introduce defects, but also you have to link that to the orientation of the crystal relative to the applied stress. And that is ultimately gives you a structure which contains crystals and defects, and these defects affect the properties. So let's think about the most common defect that one will deal with, and that's dislocations. So here's a very interesting note, description, schematic description of what dislocation slip is all about. If we had a crystal and we wanted to shear one part of the crystal relative to another, and so if we wanted to get from there to there, and these black points here are just there to denote a shear plane, or a plane at which where this part of the crystal will be in a different location for this part of the crystal. It doesn't mean that they're different atoms. It just denotes a plane in effect. So imagine we have this lattice going direct. We're looking in projection at an array, a square, a cubic array of atoms. And in principle, we could take this half of the crystal and shift it relative to this half of the crystal. But if we did all that in one action, that would be take a lot of energy, because you have to break all of the bonds, or all of the bonds here, sorry, all at the same time. And I'm going to make this pointer smaller if I can. I can't. Don't know how to make it smaller. We make all of the bonds, break all of the bonds. But if we break them all at once to shove one part of the crystal to the right compared to this part of the crystal, that takes a lot of energy, a lot of force, in fact, to do that all at once. So how materials actually deform is just bit by bit. So the best analogy is either a carpet. If you want to move a piece of carpet, if you had a flat carpet on a ground and you try to pull the carpet all in one movement, there's a lot of friction spread over the whole surface, and it takes a lot of force to move that carpet in one go. But what you can do is you can create a little ruffle. You can make it with the carpet, or you can make it with the caterpillar, whichever way you want. You create a little ruffle, and you only have to separate this part at any one point in time. And then you work on this part if you're weak like me, and you can only apply enough force to break one line of bonds. And then you can move one layer of atoms a little bit, and then you can move it again a little bit. So if you have a finite force available to you, you can just keep moving a little bit at a time, and eventually you go from this position to this position. So that's typically what happens in the movement. We start with the perfect crystal, we start to deform, and we go from there to there to there to there. So that's the simplest way to think of dislocation slip. Take note, this is something that might come up in your studies, you may come across it a lot. The deformation by dislocations doesn't change the arrangement of the atoms. There's no orientation change here. Ignore the fact that these are black. It's just a way to note where we have this separation of the two halves of the crystal. But these crystals, the atoms here, are the same orientation. Dislocation slip does not change the orientation of the crystal. Certainly not at the location of the slip itself. This slip operation, this change in the shape of the material, may affect the constraints, may affect elastically the whole crystal. And you may get some rotation or bending, kind of hard to say, but depends on the situation, depends what the constraints are. But there may be some effect just by simply deforming the crystal in changing the shape of the crystal in this way. There may be some effect in the impact on how this then fits into the remainder of the material. But for the atoms themselves, at the slip plane, there's no change in orientation. So there you go. Oh, again, a little bit illustration for dislocation slip. Let's examine what happens. Yeah, so you'll see these, but I'm skipping through the videos, which hopefully will show up. You'll see where they should belong. But you have video clips on YouTube that you can insert there as you please. In terms of FCC, the simplest slip is on the 111 plane. That's probably the only slip. And as I would have demonstrated in the videos, you take an atom which is on a B layer here, and in order to move from this B site to this B site, you have to shear in two steps, 1, 2, by what's called a Shockley partial. So in order to move the lattice and get it back into its original configuration, a perfect lattice, it actually takes 2 steps. So if we only use 1 step, the lattice is now in a quasi, if you like, crystalline state. It's not FCC anymore, because by moving that from B to C in this particular instance, that would create a what's called a stacking fault on this layer. Yeah, so typically a perfect dislocation passage is actually a little jog going using these going. We've got an atom here sat above these A atoms in the plane above it, and in order to move it using by shear, we have to actually the easiest path, the low energy path to do that is going bonk bonk. So we go to that, and I show that in the videos. I think it's quite simple. Um, and I think I demonstrated it for hexagonals there. I'm not sure if I did. I hope I did. But for the hexagonal close pack systems, I mentioned how the different slip systems have different planes of different properties when it comes to slip. And it boils down to the atomic arrangement within the planes. So they're not really planes exactly in that they're not exactly flat. They can be corrugated, slightly ruffled, but the atoms can still glide with respect to one another. So the case when it comes to hexagonals, the case I just talked about, which was for the face center cubic, is the same case for the basal plane in hexagonals. You get these two partials in the Miller-Brave notation. These are the partials. So, but we have these low energy, easy routes to translate a full Burgers vector, 1/3, 1/1 bar 2. In order to get from here to here, we go through a two-step process, which isn't exactly aligned, but it's a little jog off one off the other. And that's in the basal plane. But we can glide on prism planes. So I mentioned how prism planes can be the most close packed planes. And in fact, for zirconium, this is the most likely plane at which you would get deformation. And there's barely, in this case, there's really no, although there is a little bit, there's no intermediate site where the material might rest. So in this case, you might get a situation where a material will deform, and you deform it a little bit, and the atoms shear and then sit there, and they're happy to sit at this point. In which case, what you end up with is creating a stacking fault. But for the prism slip, it's very difficult to do that because this is a metastable state, and it's so much easier just to slip down. And so what you tend to get prism slip is no splitting of the dislocations. You never see any evidence of any partial dislocations here. And if it's pyramidal slip, a slip on a pyramidal plane, and again, you watch the videos, you'll see this, there's absolutely none at all. And it's a higher energy barrier has to go over. The interesting one is when you have C+A slip. This is the Burgers vector of C+A in, sorry, I should have explained the notation when it came to referring to the slip in terms of a lattice. I think I do talk about it in the videos, but in terms of vector notation, C+A is that vector. So if you move a distance equivalent to an A-axis, an A lattice parameter and a C lattice parameter, the vector that denotes that change, or that vector in letter form, is this one. It's 1/3, 1/1 bar 2 3. You can well understand that often when people are chatting, it's awkward to be saying, well, that's a third 1/1 bar 2 3, or 1/1 bar 2 1 3, or third something else. Often you just simply say C+A. So C+A slip on 1 bar 1 has this complicated structure. And as you would see on the videos, what that means is that you can actually, in the case of this particular system I demonstrated, you can do this partial glide on successive planes. And what that means is this can now be a twin plane. Because if you have successive planes and they all go a little bit, and this partial dislocation, and then they sit comfortably at this position, that would be a twin, in fact. So you have each successive plane of atoms, you have another one and another one, and they can all go in the same direction. And I showed in the video how you can't do that for this configuration on the basal plane, because if you move one layer and then you try to move the next layer above it, the next consecutive layer in height, there's a barrier to the movement. There's no easy route through in the same direction. Kind of difficult to conceptualize, but that's where the ball models help. Likewise, if you have some of these other obscure planes, this is not a normal C+A slip plane because it's a huge energy barrier. This is the easiest C+A slip. But in terms of twinning, you could do that on successive planes, and that would be a reasonable twin operation on 11 bar 22, which is another plane. Likewise here. And there I can show it in the ball models. Oh, now I get into BCC. Sorry. So I don't know why. You can have the same thing in a BCC structure, which I just showed the videos. Maybe I'll move them around a bit. But in the BCC structure, you also have this possibility of twinning, even though it's not a close pack structure. So this slide just summarizes the number of slip systems that's possible, number of distinct planes and directions on which you can slip in an FCC case. So there's lots of opportunities for shearing by dislocation slip in the FCC case. In the hexagonal system, this simple ball model glide, which is equivalent in the hexagonal case, that is equivalent to that. You only have three possibilities on that plane, or three possibilities on the prism plane in this direction, or on the pyramidal plane in this direction. And this, especially when, and sorry, what I was going to say is, what I don't have here is the C+A slip. I should have put that on, because C+A, which is, these are all equivalent slip systems, which are equivalent to this one. It's only the A-axis slip that I'm thinking about here, this one. But we have others, and I realize I've made a mistake in not including that in the slide. Here's an illustration to show what are the common slip systems in the various materials, BCC. This is the one I described. There are others, depending on what element you're talking about, which are essentially always a 1-1-1 direction, but they can be on slightly different planes. The only one I've looked at right now is the 1-1-0 plane, but there are these other options always in the 1-1-1 direction. Likewise for the FCC, it's always in the close pack direction, the shortest lattice distance. And in this case, it's a 1-1-0. In the hexagonal, even though that this particular slide shows the A direction, the 1-1 bar 2 as the predominant slip system, because it's the shortest bond length, that really only applies to a perfect stacking. That's either close to magnesium or zinc and cadmium. The reality is that the slip systems in hexagonal close pack metals vary quite a lot, depending on what material it is and what the purity is. So there are a number of different options in the hexagonal system for slip. The three most close pack planes are the 1-0, the 1-1-1, and the basal. And for zinc and cadmium, it's basal. For zirconium, it's 1-0 bar 1-0. Sorry, it might be a 1-0 bar 1. I worked this out once, but it might be 1-0 bar 1. I think it's, oh, it's 1-0 bar 1, except it's corrugated. The complication with the hexagonals is if you can see here, this atom here, which is part of the 1-0 bar 1 plane, is actually not in the same plane as these atoms here on that define the face of the prism. There's less corrugation for this plane, for what's called the pyramidal plane. This is the prism 1 plane, pyramidal plane, basal plane. And this means that there's some ambiguity sometimes on what is the easy slip. For sure, for the 1-0 bar 1, I think I showed in one of the videos, this corrugation prevents slip in any C direction. But the corrugation is kind of so light, or is less prevalent for the 1/1, and so in fact on the 1/1 plane, which is this one, if I can draw it with my pen, which is this one, the C+A slip going from here to here is much more feasible for this plane. That's the only way to get, in terms of slip, a C component in your deformation. It's a C+A3. It's some combination of C and A when I talk about C+A. Prism 2 plane is the 1/2. This is a plane that will show up quite a lot, but it's not a close pack plane, and neither is it a slip plane. But the direction, which is the 1/2 direction, is a slip direction. So for most hexagonal metals, which includes titanium, zirconium, you can have a lot of variation in what are the slip systems, but also the twinning systems. So here's the description of the various slip systems that exist in HCP. The one that I'm most familiar with is this, in terms of a C+A slip, is this pyramidal first order one. It's the easiest one to make a ball model out of anyway. But you can have slip on the prism plane in an A direction, or slip on the basal plane in an A direction. In zirconium, this is more prevalent. In magnesium, this is more prevalent. And I think I illustrate this in the ball models. The ball models are more applicable to the perfect stacking of spheres, which is closer to magnesium than anything else. There are other options for deformation, for shear deformation, which is twinning. And as I'll show you in the next couple of presentations on the video, although they won't show up in this recording, you'll have to look at them on YouTube. The stacking in the hexagonal system is not conducive to shear, twinning shear on basal planes. You may shear on one plane, but the next successive plane, which is necessary to have a shear operation, the shear of the partial is blocked. In this case, it would be a 1/1 partial on the basal plane. You can't get successive shearing on successive planes for the basal plane, but you can get successive shearing on other planes, such as this one, the 1/1, or these others, but I'm going to demonstrate it for this one. So here are the embedded videos that you won't get, but you can go and look up. Slip versus. So what about twinning on the base? Different twinning in various materials. Taking a step back now, here's some examples of slip in Inconel X750, which is an FCC structure. What we have operating here, shown in a TEM, are two slip systems. One which is inclined to the orientation in which you're viewing it. It's the projection. You're looking at TEM form. We're looking at a slip plane which is inclined to the direction in which you're viewing it. But there are some slip planes which are parallel with the direction of viewing. So what you see then is on slip plane, you see the dislocations in projection, shown here. And for the other system, the other slip plane, slip system and slip plane, these lines here represent these dislocations, these curly dislocations we see here, but viewed from the edge. So what do I mean by that? Well, you can take a thin foil and take a slice through a slip plane, in which case you take out the different, you're actually capturing segments of dislocations from a slip plane. And when you look at it in a TEM from above, you see the segments of dislocations. But if you look at it edge on from the side, you see that these segments, which are viewed here as a finite length, these curved segments, they just appear as lines. So it's just as well to understand what's going on when you're looking at a TEM micrograph, because to understand what it is exactly you're looking at. So when it comes to slip, what you're looking at is a slice. So if this dashed line here is represents the bulk, what's going on in the bulk material, and what you have is dislocation glide happening, dislocation slip across a slip plane, which is a translation. And then you make a thin foil out of it. So you're just basically cutting a slice of material out of the sample. And then you're looking at it. And what you see is this segment of these these dislocations on this slip plane, which see in these segments in projection. In this case, they're inclined, but this is how it actually, that kind of thing actually looks in terms of a TEM image. Previously, you might have noticed some notes about cracking happening, and that's basically refers to a fallacy that exists about what this line, this imaginary line, what it actually means. It has no meaning. Until you've created the thin foil and created this imaginary intersection of the slip plane with the thin foil surface. So in the bulk, it has no meaning at all. But it might show up, and people might think that it actually corresponds to something real, but it doesn't, because it's an artifact of actually selecting your slice. I should have put this slide in earlier, but basically this is the schematic which illustrates two different types of slip. I showed the little passage of the caterpillar or the carpet to which showed how the mechanism of dislocation slip involving in dislocations, where you create a little ruffle on the plane, and you can progress this extra half plane, you're only breaking one line of atoms at a time until you shuffle the whole thing, whole half of the crystal, by one Burgers vector, one lattice parameter, or one Burgers vector, in fact. But there are two modes in which dislocations can be introduced. One is edge mode. Basically, if we pushed half of this crystal in this direction, you could shear it just by breaking a line of bonds here and pushing the extra half plane across the crystal. The other mode is it's the same shear, but you start at one edge here and you break a line of bonds along this line, and then you tear the material in a line going across that direction. So the directional motion of this dislocation is one direction, but the net shear, like tearing a telephone book, the net shear is in at right angles to this in the direction of the Burgers vector. So a screw dislocation has a Burgers vector along the line of the dislocation, but the direction of motion is perpendicular to both. For an edge dislocation, the Burgers vector is perpendicular to the line of the dislocation, but in the direction of motion of the dislocation. They both give the same shear, but the two types of dislocations. The other way to create shear deformation is through twinning. Twinning is far more prevalent, I think, than people appreciate. And what we have here is an illustration of what goes on when you're twinning. This is a tensile specimen. So if you have a tensile specimen and you have a slip plane here, and you break all the bonds of the dislocations along this line, along this plane, you can shift the crystal, parts of the crystal, with respect to the other. And then this shift, as you will see, causes this displacement, but it leaves the alignment of the crystal, ignore this black line, it's fictitious, but this alignment is the same. So it doesn't change the orientation of the crystal. Twinning, on the other hand, if you do a similar kind of shear operation, as you would by having multiple shears of perfect dislocations along a given slip plane, in twinning, you do change the orientation of the crystal as illustrated here. And we'll talk more about that, and I'll illustrate that in the videos. So in summary, basically, slip amounts to this kind of deformation. You take a block of material and you pass a dislocation through it, and it shears the one part of the crystal with respect to the other. Damn it. And I'm going to talk backwards. What happens when you get a twin is you shear, starting at the twin plane, you shear each atom successively a little bit with respect to the layer underneath. So you can progress a twin, you can move a twin, but it's kind of like a screw in that the deformation is going this way, but no, it's just a twin. Sorry. So what's important to know about the twin is that you're only, although that you're progressing this partial dislocation along this direction, it's a partial dislocation. I should point that out. But you're only moving one layer of atoms a little bit with respect to the layer underneath. So although we get this amount of deformation over here, we're shifting something from this point to this point. It's a gradual accumulation of little shears from each successive plane. Here's another illustration. We're looking at the 110 direction. The twin shear direction is 112. The perpendicular, the twin plane is 111. I'll be talking more about this and illustrating it in the videos where I can do that with the ball models. And this formally is what describes a twin operation. We have a twinning plane. You have a shear on that plane and all the successive planes above it. But there is an invariant plane, which is this one, which is common both to the crystal, which is the base crystal, and the crystal that's sheared. So they share this one invariant plane, which is in the direction of the shear. And they also share a common plane, which is this twinning plane. But for all other directions, all other twins, all other directions and planes, they're different. So a twin can be coherent or incoherent. So this is an example of a coherent twin where if we're looking along a 110 direction, along the 111, and this is the 112 direction, which is parallel with the 111 plane, this represents what happens to the arrangement of atoms looking along the close back direction, the 110 direction, in the parent crystal and the twin crystal. But sometimes this boundary may not be exactly aligned with the symmetry, the mirror plane, which defines what the twin is. And it could be inclined that way. This was lifted off the internet, and these authors chose to identify a common rotation axis, which is 60 degrees. And that just means that it shares what they really should have said is just that it's a 1-1-1 plane along here. And this common rotation axis isn't a true rotation axis, it's a rotation axis in projection, and comes about because when you have close back spheres, you have this six-fold symmetry. But when you're looking along a 1-1-1 plane, the six-fold symmetry only exists for the 1-1-0 planes, but not the crystal. The real symmetry of the crystal is a threefold symmetry. And that would be 120 degrees, not 60 degrees. So this is partially correct, but really, ideally, what the author should have said is that this is a common 1-1-1 plane, in which case everything else falls into place. Here's some videos talking about that common rotational axis. Oh. Trying to get through it. So there were some videos describing twinning in FCC. But what about BCC? This applies to ferritic steels and or beta phase in circulating pressure tubes. So in a BCC, I'm going to pick one specific slip plane, is this one, and the slip direction is the close pack direction. In a BCC, it's the 1-1-1 direction. And you'll see the arrangement of the atoms on that plane, and it's not close packed. It's not exactly like that either, but I think they've just drawn it weird. So this is a better rendition of what's going on in a BCC. This is a better schematic. But basically, where the atoms sit on one layer with respect to the next, given that the close back plane is 1-1-0, in order to shear a bottom layer of atoms, one layer of atoms shown here by these two circles here, relative to the bottom layer of atoms, the atoms actually start here. They sit on these sites, which is not, if you like, a low energy site. When it comes to ball models, at least, and then they shear in 3 steps, 1, 2, 3, to bring this ball in conjunction with that ball, which is the 1-1-1 displacement, and that's shown here vectorially. So here's a schematic showing body center cubic and slip, the system I just described. We're talking about slip on the most close back plane, which is the 1-1-0 plane. And so what we also have in the BCC is the possibility of a Martin-Siddick transformation. This is a little bit harder to describe, but if we imagine a structure like this, which can think of for in effect a body center cubic lattice, and we can draw on what would be an orthorhombic lattice on top. And if we take these atoms, this one, that one over there, and this one, and shear them a little bit one way, that will then end up bringing the material more into a hexagonal arrangement, which is closer to an FCC. So with some slight readjustment in lattice parameters, you can actually do a transformation in principle according to this diagram I got off the internet, in principle, you can translate the BCC, which you can represent, in this case, as an orthorhombic cell, translate the BCC into an FCC structure. So let's move on now. I don't want to dwell on that too much because, we're going to get back into that. So all of the shears that I've been talking about, the bulk shears I can be talking about, have been identified and characterized by this guy, Muir. And this is fundamentally, there are 4 different reactions that he's talking about, or that he has identified. If you're starting from a FCC structure, bearing in mind that this represents the A and the B and the C atoms, we're looking, I guess, on the 1. Yeah, I guess we're looking down the 111 kind of plane. Not sure. Anyway, not sure what orientation we're looking at. You can create a stacking fault by shearing. Sorry, so that's a 111 direction. And in this particular case, I'm not sure how yeah, sorry, we obviously in the twin case, it's the 112 direction, which we're looking at. So we must be looking in a 110. We're looking in a 110 projection. And the shearing direction is a 112, which is a Shockley partial, which is that very easy glide component that I showed on the ball models. If you just sheared individual planes a little bit, in this case, if you like, yeah, instead of, sure where the shear would be, there, this one. So we sheared this sheared here, this plane, along this direction. That creates what's called a stacking fault. So you can see how, instead of being all nicely arranged, the atoms here in the 111 directions, they're actually a little jog, and that's a stacking fault. If you apply that shear rather than just on one individual plane, which would create a stacking fault, but in a bulk, we apply it over numerous planes successively, the same shear, all in the same direction, we end up with this arrangement here, which is a twin. If we sheared successive planes, sorry, alternate planes, not successive planes as we have in the twin, we do alternate planes, then you change the crystal structure from gamma FCC to gamma or epsilon, sorry, gamma epsilon, which is a HCP. There's then a slightly easier shuffle, although I showed you in there was a BCC to FCC transition. In this particular instance, what this guy Muir has devised is a FCC to BCC transition that involves an intermediate hexagonal structure. Don't want to get too wound up on this, but just that so you're aware that there are these bulk transformations, which can either be a martensitic transformation here, or it can be a twin transformation. Just want a simple shear. It's a fault. You create these stacking faults, and this is in addition to regular dislocation slip, which is 2 of these shears that would give a stacking fault. You have 2 partials, which give you a direct displacement. So an issue that was posed by one of your predecessors was that the question, can dislocation slip affect the crystal orientation? Now, in some circles, people think it can, but what happens, I think, is that there's a misunderstanding about what is an orientation change that happens both elastically and plastically. So I've already indicated that dislocation slip is a translation, and why do people then talk about orientation changes from slip? So I'll try and illustrate that now. If you look at a simple tensile transformation, sorry, tensile test, and we're talking about dislocation slip, let's say we have these slip planes here, then what happens when you deform the material and if you have a large amount of slip, the load line will actually get shifted over to this direction. But the load frame is going to want to pull in this direction along this load line. So what happens is that in order to conform with the tensile machine, the sample has to be bent back into register with the load line. But this bending, although it was caused by essentially shear deformation, actually, which could be slip or twinning, it doesn't matter. It's some way of deformation. This bending is caused by that. The bending itself is an elastic distortion that is caused by the constraints of the machine. So if you work out in a typical tensile specimen what that stress is and what the distortion is, then it's actually quite small. So the elastic distortion typically is less than 0.1%. And more importantly, once you've demounted the specimen, it will, if you like, it will, without the constraints, without the stress bending it, it will take up this shape. And the distortion, the distortion that exists here, the elastic bending that exists here, no longer exists once you've demounted the specimen, or if you take a slice through it. You relax the stresses caused by this constraints. And this often gets mistaken. This gets confused. People have cited this kind of elastic distortion as an excuse to justify the notion that dislocations cause a rotation of the lattice. Dislocations do not cause a rotation of the lattice. There's only a rotation of the lattice. It's an elastic rotation, and it has to do with the constraints. Once you've created the specimen, an X-ray diffraction specimen or TEM specimen, you're back to this situation where the constraints have been relaxed. And there should be no resulting elastic distortion, except you might get some intergranular stresses. But recognize that as an intergranular stress distortion, not as a distortion due to dislocations, because the crystal orientation either side of a slip plane should not change. There's no physical possibility for that to happen. If you want to calculate what the stresses are, it's very simple formulas here. The stress for any component or anything that's a bent beam, if you like, is a function of the distance from the neutral axis and the radius of curvature. So if you look at the radius of curvature and the thickness of the specimen, so assuming the neutral axis is in the middle of a specimen, one can easily calculate what the strain is. So having given that, knowing what the strain is, or knowing what the angular distortion you might get, and what the bending radius, or if you like, the radius of curvature might be, one can easily calculate typically what the strain would be. So tensile test, what happens is you might get some distortion, elastic distortion of the lattice, but that is relieved by the generation of a new slip system. So if you have one tensile specimen and you get slip happening like this distortion will build up until you reach the yield stress of secondary slip systems. And this distortion, the amount of lateral strain, the torque that one induces, the torque that one induces, in the bending stress that one induces, if you like, in the material until we get the operation of alternate slip systems to essentially bring the load line into parallel with the orientation of the specimen, is this strain, if you can call it a strain, is of the order less than 0.1% when you get to the yield point. So the yield point is typically anything between 200 and 600 MPa. And when that happens, that can happen due to these constraints. The constraints caused by slip on one system can induce secondary slip as you're pulling on a secondary slip system to keep the tensile specimen aligned with the load line of the load frame. So this here shows slip on two different slip planes, and that's typically how a tensile specimen will operate. That's graphically illustrated when it comes to the stress strain curve. And here's a stress strain curve for a zircaloy 2, which is actually being irradiated. And what this illustrates is the operation of what are called channels, dislocation channels. And I haven't talked about that, but I think I might at some point. Dislocation channels involve the gliding of dislocations through volumes of the crystal and the interaction of these dislocations with hardening centers. Now, it has to be a dislocation loop. But what happens is that the gliding dislocation, like this, interacts with the loop, subsumes the dislocation loop into the extra half plane, if you like, of the dislocation, and carries on and essentially sweeps the loops out of the material. It only applies to loops because it has to be a loop which can essentially conform with the Burgers vector either by dislocation reaction or have exactly the same Burgers vector as the gliding dislocation. When that happens, you create this softer channel. So now it is easier to deform because this is essentially annealed material. And what that shows up as a load drop. So it's less stress to create strain. So we drop the stress at this point. It's not true stress, of course, it's an engineering stress, but it would still manifest itself even on a true stress strain curve because you're essentially softening the material. And as we described earlier, with that secondary slip system to bring the tensile specimen into conformance with the load line, you then have options for a second slip operation, the introduction of a secondary slip system, and to bring it into conformance, and this generally shows up as a second load drop. And there we see it. And eventually the material will neck and fail. So one way to illustrate, to give an example of why slip alone, slip categorically does not change the orientation of the crystal, is to illustrate this with some deformation of a plate where we can look at the texture changes. This is a kind of a cruder engineering way of looking at this potential for orientation differences. So we have some zirconium plate, which has a very strong texture with the basal poles in the transverse direction. And what this graph shows, we will be getting into textures, but I'm going to have to assume that you all understand a little bit about what a texture or a pole figure is right now. So what happens here in terms of the texture, the pole figure shows orientation differences in the distribution of grains in a given sample. So this top line here shows that if we do what's called a direct roll, we roll in the longitudinal direction, that in this case by roughly 25%, if you go from this orientation distribution of the material to this after 25% rolling, you can see that there's no change in the texture, nothing discernible anywhere, nothing of any worth. So, and that corresponds to this line here. However, if we rolled in the transverse direction, which is exciting a lot of deformation, shear deformation in the direction parallel with the c-axis, we get a significant amount of orientation change. And this comes about because we have this possibility of twinning on planes which are not in the basal plane. Planes which are like the 1 bar 1 1 or the 1 1 bar 2 2 or whatever. These are, I've described earlier. These are shear operations on other planes which are inclined to the basal plane. And these twinning operations create change in orientation, as we see here. So what's going on can be demonstrated schematically here. In the case of what's called the direct roll, we have a predominance of grains with this orientation, and the longitudinal direction is the direction in which the material is being deformed, primarily, not exactly, but primarily. And when you have this situation, what that means is that you end up exciting these two slip systems. And they're prism slip systems. And it's these two as opposed to this third one. And what that means is that you end up with no orientation difference because slip does not change the orientation. It just shears, it's a translation, it just shears one part of the crystal with respect to the other. Okay, well, that's enough about deformation. We'll get on now to talk a little bit about diffraction principles. And I just want to introduce it, although following lectures are the ones that will have more about diffraction primarily. Spend a lot of time in this lecture focusing on crystal structure and deformation, and that's so that you have the grounding to understand what is needed, if you like, what you will need to understand when you're applying diffraction principles to characterize a material. In order to make the most of the characterization, you have to understand what you're doing and what's in the material. So as you can see, the two main sources of radiation that we use to probe matter at the atomic scale are electrons and X-rays. So X-rays have wavelengths that are around about 1 angstrom. Electrons have a wavelength which is much smaller. And this gives us the tools to probe matter, probe on the atomic scale, and basically get to understand or certainly to characterize the material, the microstructure of the material. Whether it's the crystal structure on a broader scale or whether it's the defect structure, which would be the dislocations primarily, but could include twins. And what we're interested in often is the orientation of the grains and the accumulated orientation of an agglomeration of grains, which may include some twinning going on, especially after deformation. And the defects that exist within the grains, which also change the properties. So you not only have the orientation, which affects the properties of a component in a particular direction, but we have the internal structure, which also affects the properties of the material. And we use X-ray diffraction and TEM analysis. Again, this is by way of introduction, so this is just slide illustrates what are we talking about. In TEM, we're using scattering from a sample. We have a sample at this level. Here we shine electrons through it, and we can, in the case of electrons, the beauty of electrons is that they're electrically charged, obviously, and because of that, you can use electromagnetic lenses to basically focus, distort, affect the refractive index through which these electrons are passing. And in that situation, one can create different modes of examining a material. In the image mode, we can look directly at the microstructure. We have a real picture of real space, what's going on in the material, albeit in projection. We're shining light or electrons through the material, and we're looking at the projected image. So this may be a bulk sample, and a lot of these defects here may be lying sometimes at different heights within the sample, but we're seeing the projected image here. Or we might want to be interested in the diffraction, the effect of the crystal structure itself on the scattering of the waves. And I'll talk a little bit about the diffraction principles next. But in the microscope, one can examine, just accept for now that a crystal structure, one of the things it can do is it can, when electrons or X-rays are scattered off in certain directions, you get what's called constructive interference. And what happens then is that these electrons, when they're detected at a certain point, the ones that have been scattered at a certain angle, you can see certain points of high intensity. So there is more chance that more electrons get scattered off at particular angles and can be focused to a point on a diffraction pattern. And that reflects this phenomena where we get constructive interference for those waves that are scattered in certain directions. In the case of a X-ray diffraction, it's not quite. So with X-rays, it's slightly different from a TM. In the electron microscope, we're shining electrons through a sample, and although they're scattering off the planes, the angle at which the electrons are being scattered is typically a fraction of a degree, and that's what we're interested in. But in X-ray, the scattering we're interested in comes out at very high angles, 20 to 70 degrees, for instance. And what we're interested in is essentially the characterization of the material. What allows us to characterize the material is that different atomic arrangements result in the scattering of X-rays in particular directions where they're coherent, if you like. So an X-ray exiting at this point, hitting a sample here and being detected at this point, for certain arrangements of the atoms in this crystal, it will be coherent with a similar X-ray coming to this point and then being detected at this point along a different ray path. But as I'll show you in a minute, these different ray paths are consistent with, in the case of a Bragg diffraction, you have to have, so long as the angle of incidence of this point and the emission and detection is the same at the center of the specimen, these path lengths are such that a coherent wave here is also, or two waves which are coherent here are also coherent here. just the nature of the geometry, which I'll describe in lecture 2. But depending on what the diffraction angle, the point at which we get this condition, this focusing condition, what's called a focusing condition in Bragg-Brentano focusing diffractometer, the area over which we have this focusing condition applied changes depending on what the diffraction angle is. More about that. So what we're really talking about when it comes to X-ray diffraction is we're looking at path differences. We're looking at the scattering of X-rays from different points in the sample, and what the wave difference is, what the wavelength difference is, how the X-rays superimpose, how you get, whether you get constructive or destructive interference. And you probably did this in high school physics, so you probably understand what I'm talking about. But ultimately, I'll be talking more about this in detail in lecture 2. Here's a schematic showing simply what's going on. Now, I mentioned in the Bragg-Brentano case that you have X-rays coming from a source, hitting a sample, and being detected at a detector. And they're not all at the same angle. They're all diverging at different angles. But what you'll notice in many texts on X-ray diffraction is often depicted as a plane wave of coherent light, or X-rays in this particular case, coming in, striking atoms, and being scattered away. So the reality is that that's not what is actually happening. What is actually happening is that you're getting light coming in divergent paths and being scattered off and being detected over here somewhere. So the point about it is, if you follow through the path lengths for example, in a Bragg-Brentano focusing condition, path lengths for waves coming from a source to a detector and scattering off atoms within a material, the path length is the same as if these were parallel waves coming in, a parallel plane wave coming in and being scattered. So one can substitute, for ease of calculation and for ease of demonstration, one can substitute this kind of condition and say it is equivalent to having X-rays coming in and striking the material like this. One other important feature is that the angle of incidence has to equal the angle of reflection. What that means is, if you just think about one layer here, and this this wave train coming in and striking the surface at this point, this same wave train coming in and striking the surface at any other point and being scattered, when the angle, or you're sampling the scattering coming off at a certain angle, when that is the case, then it is also, if you had two wave trains coming in, striking the surface at any point, not just at the atoms, but at any point, if they're coming in at a certain angle and they're coherent, and we examine them, the waves coming off, the two trains coming off at the same angle, they will also be coherent. I realize I haven't demonstrated that on this figure coming off the same plane, but I do in lecture 2. I talk about that in lecture 2, so you'll see it. For now, you just have to accept that that's the case, and the condition where you get, for a plane wave coming in and striking an array of atoms and being scattered off, also coherent, that condition, and that corresponds to a peak, if you like, a constructive interference. We see a strong diffracting signal here. In that case, that corresponds to the Bragg condition and Bragg's law, where the difference in the path length of this plane wave coming in and this plane wave exiting, this path length difference here is given by 2d sine theta. So d sine theta and d sine theta. And so long as that path length is some multiple of the wavelength of the radiation, we have a strong, coherent, constructively augmented, if you like, signal coming off. And the art of X-ray diffraction amounts to, in part, scattering of different layers of atoms. You're only scattering off the atoms that are really there, and sometimes you may have planes which actually don't exist. In which case, that's getting a bit obscure, but you don't actually have scattering off the waves. But just like I said, we have a parallel wave train coming in, and it's not real, but it's just one thing that we use for illustrative purposes, or makes it easier to do the calculations. In the same way, one can have imaginary planes here, which you can say are scattering, but what it amounts to is you're only getting scattering of these layers of atoms, but scattering off an imaginary plane halfway in between, for instance, can be envisaged simply because it's a different, would then correspond to a different orientation, a different Bragg angle. These wave trains coming in at a different angle, and ultimately it might mean that you have a difference here in the n value, the number of wave lengths that are encompassed in this path length difference. This will make more sense in lecture 2. And I also talk about structure factors. The thing that people use to characterize structures, especially powders and stuff like that, is a thing called a structure factor. I'm not going to go into the details here, but what this amounts to is we have a position of an atom in a unit cell and a vector which describes the scattering off a given plane of atoms, and a factor which is the strength or the intensity of scattering from an individual atom. And the intensity of scattering for a given plane, for a given arrangement, this is the sum now, given arrangement of atoms within a unit cell, is given by this expression. And I'll talk about the derivation of this expression in lecture 2. But basically, if we have a plane HKL and atomic positions xi, y, and zi for each, and we sum up all of these intensity variations, we get a strength of scattering, a strength of diffraction, which is the structure factor. It's very important in terms of characterization. Again, this is an introduction, so I'm not going to go into the details too much, but one of the things that will be coming up a lot is that what we're talking about is probing real space, atoms which have a density in a certain plane, which it's characterized by a certain density also, but also plane spacing. And we're probing this electron intensity distribution in real space with radiation, with waves. And in doing so, what we're actually doing is transforming from real space into diffraction space. So diffraction space is the Fourier transform of real space. So what that means is that if we have a characteristic angle for diffraction, so there's a characteristic angle at which all of the waves constructively interfere to create a point of intensity here, where we have all of the waves coming up to give a strong signal. The point that which that occurs is a function of the angle. But it can also be envisaged as if you're in an electron microscope, it's a point on the diffraction space, which is a point. So just in the same way that you have, so that I'll show you in the next slide. So we have a diffraction at a certain angle, which we can envisage in terms of diffraction space or angular space as a point in angular space or diffraction space. They're all interchangeable. They're the same thing. But basically, it acts like in the case of a Fourier transform, it means that we're converting a spatial variation. So if we have a spatial variation in electron intensity, a real spatial variation that exists because of the arrangement of atoms, that spatial variation transforms into a reciprocal variation in intensity and diffractive intensity in terms of diffraction space. So just like a Fourier transform in the time domain turns out to be a frequency in just as a Fourier transform of a time domain, a periodic time variation, a periodic variation in something, in this case, spatial variation, this periodic variation transforms into a frequency in when you represent that as a Fourier transform. So T converts to frequency, and this frequency is equivalent to this variation represented by 1 over D. So time in one mode becomes 1 over time frequency. In the same way, in spatial variations, a space dimension variation corresponds to a reciprocal variation in dimension in the Fourier transform space. So this spatial variation, when it comes to arrays of atoms, you can pick a plane of atoms here. It'll have a spatial variation electron density shown here. Or you can pick this plane of atoms here, and that'll have a spatial variation shown here. Or you can pick these planes of atoms, and that'll have a wider, let me draw that in. That'll have a much broader, spatial variation. Drew this kind of crap. Damn it. So we have this broader spatial variation here. If we look at this in terms of electron density. God, I'm not very good with this mouse. So anyway, we're sampling. We're using lambda, which is a different wavelength compared to this variation, if you like, this spatial variation in electron density of the material. We're using radiation, X-ray radiation or electron radiation to probe and sample these variations in electron density in real space. And again, more on that in lecture 2. Here's just a throwaway item just to illustrate what diffraction can give you, what it looks like if you were to image it in an electron microscope. And in this case, this shows how it's on a convergent beam. You're looking at convergent light, which is closer to the case of the X-ray system, where we don't have parallel beams, we have a non-parallel beam. And then we're collecting the intensity coming off. So if you like, nah, I'll just leave it at that. This is the non-parallel beam, and this is the parallel beam. And this is what diffraction looks like in an electron microscope. And what we're seeing here is the effect of scattering, in this particular case, over a large angular range. Let's say 20 degrees, there to there, 20 degrees from here to here. Maybe slightly smaller angular range here. If you're an electron microscopist, you may be familiar with this. This is a Kikuchi map, and this is basically a guide to how to navigate in orientation space. So we need to, these diffraction patterns in an electron microscope that you collect are real time. You can think of them as being attached to the crystal. So if we're looking directly through a crystal in the electron microscope along the C-axis, this is the diffraction pattern we would collect. And when we've got this diffraction pattern, we know we're at this orientation. We're looking directly down the C-axis. And if we want to move to another orientation, say a prism orientation up here, what we would do in the microscope in real time is that we would tilt the sample so that the orientation changes and moves us up this set of tram lines over here till we get to there. So it's kind of weird because it's not a spatial variation now. In this particular instance, it's an angular variation. When we're in this mode, we're actually in the Fourier transform of real space. So we have to think in terms of angles. And that's what one does. One navigates around in reciprocal space. So reciprocal space is simply angular space because of that relationship. N lambda is 2d sine theta, or you can think of it also as 1 upon d is 2 sine theta over lambda. So the magnitude of this area, if you like, is a function of lambda, but is ultimately this intensity variation is a function of the angle, sine theta. Again, this is simply by way of introduction, so I'm skipping through this very quickly. When you have, it's one thing to think about single crystals and the properties of the single crystals and the defects and what the defects within those single crystals do to the properties. But ultimately, when we're talking about a component, such as a tube, the properties of the tube come about because of the cumulative effect of all the grains in a polycrystalline sample. Now, typically in a pressure tube, there will be a preferred orientation. If this hexagon here represents the orientation of a typical alpha phase grain in a piece of pressure tube, or there are many, many more grains which are oriented such as their C-axis is parallel to the transverse direction, and this is represented on a pole figure such as this. And this just gives you an example of what a pole figure is. In lecture 3, we'll be talking more about pole figures and how we use the information, how we can condense that into texture parameters and such. I'll also, in lecture 3, be talking about different methods of combining or obtaining information on texture. Historically, inverse pole figures and full pole figures using X-ray diffraction have been used. Neutron diffraction is another way in which pole figures can be put together. The processing is another thing. But in the last 10 years, I would say, maybe 10, 15 years, benefited from the the introduction of electron backscatter diffraction. So basically the orientation of a grain in a given structure can be obtained by collecting the Kikuchi maps, those orientation maps that I showed you earlier, for each individual grain, and then matching that up, the orientation obtained from an SEM with a grain, and plotting that on a pole figure, as you see here. So what you can see here is on this pole figure, there are a number of grains, these platelet grains here, which tend to have their orientation out in the transverse direction. The fatter grains here tend to be clustered around this orientation. We've kind of known this for a long time, but this is just a confirmation of it. It just shows you how the texture is built up. So grains which are more equiaxed tend to have a strong radial orientation, and grains which are more platelet-like tend to have a strong transverse orientation. Just to illustrate what that means is that grains which tend to be more cubic, if you like, more equiaxed, tend to have this orientation relative to the radial, longitudinal, and transverse directions. And grains which are flatter tend to be more like this orientation, the V atoms. However, it doesn't mean to say that that's exclusive. So you can get some fatter grains with this orientation. And you may get some the blue grains, which tend to be flatter. So flatter and fatter grains, there's a mix, but the tendency is to get most of the red grains, most of the platelet grains tend to have this orientation, the B ones. So B here. Oh, sorry. This is predominant, and also this. In terms of volume, about 50-50, about half and half of the volume is comprised of grains with this shape and this orientation, and 50% roughly of grains of this shape and this orientation. Although you do get more of a mixture in this particular instance. If you look down here, you get some of the blue ones. They're the ones which have this sorry, yeah, the blue and the green correspond with A. Oh, so actually, sorry, correction. This is very much dominant orientation in this particular case. So although I've put the A grains here, it's actually a mixture of A and B. So for the fatter grains, we have a mixture of A and B. Sorry, no, we don't. The B would correspond to the red. So I'm sorry, there are some reds there. Enough of that. We're going to be talking about texture later on. This just gives you an idea of what to expect in terms of texture for zircaloy components. You can have a range of textures depending on how the material was manufactured. So things that tend to distort the material and change the texture also distort the grain structure. So we have to be aware of the grain shape and size. And where this comes in terms of properties, one is often concerned with what the accumulation of the properties of the material. what that does. What is the cumulative effect of a polycrystalline material when transformed into the component orientation, RT and L in this case. So in this case, I've shown, I'm showing strain rate and stress for creep, for instance, but it could be any property. I mean, it doesn't have to be strain rate. It could be thermal expansion. And yeah, it could be thermal expansion. Oh no, if it was a relationship, sorry, it would be stress and strain rate are the two simplest relationships where we can relate two tensors. But anyway, the accumulation of the strain is a function of the volume fraction. And so we need factors. We need to know how much volume fraction of each grain there is in the material. Oh man. Okay, here's some references that you can look at. I'm sorry, I'm not going to repeat that. A little bit garbled in places, but it'll serve as a reference and might remind you of some of the things that were said. I think the primary things that were of use out of this lecture is basically to introduce what crystal structure was, and also to show, using the ball models, typical deformation processes that exist in FCC and HCP materials and BCC materials. Diffraction will come in lecture 2. There'll be more emphasis on diffraction. And in lecture 3, we'll get into texture and also line broadening and processing of information, that diffraction information from line profiles. We're going into more detail about what the diffraction, what information we can glean from diffraction. And that is all. Thank you.